matter exists in three phases: gas, liquid and solid. And there is a remarkable difference between the three states of this matter. Gas having no shape, no size. When it has been kept in a container, it totally fills this container. While this liquid is having no shape, but having a volume, having a definite volume. Liquid, whenever present in a container, it takes the shape of this container. While in case of solid, volume and the shape both are fixed. So, first of all, I like to start with this gaseous state of this substance, and it is the Bernoulli in 1738 introduced the kinetic theory of this gas. Now subsequently it has been developed by the Joule, Clausius, Maxwell and Boltzmann within the year of 1845 to 1898. They have developed this kinetic theory of gas. First of all, I shall say something about this theory. Theory is just the imagination. Theory is just the imagination. It is based on certain postulates. However, the postulates are experimentally verified. Then all the postulates, with the help of all the postulates, we can have one mathematical equation, mathematical formulation of that theory. And mathematical formulation becomes such that which we could not determine by means of experimentally from this theory or from this kind of equation, that we can predict, we can calculate, we can assess. So the kinetic theory has similarly some of the postulates, or you can call assumption. Postulates, or you can say assumptions. So there is various assumptions. Say, I shall limit within the 7 postulates how the gas is made of. You see, the gas is composed of the teeny particles. Now, after the mention of after the Avogadro, these teeny particles are called the molecules. For a particular gas, all the molecules have the same size and same mass. However, different gases have different masses and different sizes. This is the first postulate. And if we go to the second postulate, how the molecules are behaving, how the teeny particles are behaving within the gas. The molecules are moving at a random fashion in all possible directions with equal probability. Having the molecule can move with a variety of speeds, in all directions, and no directions has a special preference. Every directions are equally probable, and some molecules are moving very fast, some molecules move very slow. This is the second postulate. First postulate, how the gas is composed of. Second, how the molecules are staying within this vessel of this gas. And the third one, the gas molecules are assumed. This is very important. The gas molecules are assumed to be point masses. Point masses means having a definite mass but no volume. This is rather hypothetical, but you can say the vessel or the container within which these gas molecules are present in comparison to the volume of this container in which the gas is present is very, very large in comparison to this to the size of these particles, size of the molecules. And so the actually molecular size is very, very small. The distance travels the molecule in unit time. So it is rather the assumptions, ideal conditions. And the fourth one is also very important for ideal system. Ideal system means whenever the gas behaves very soberly, each molecule, there is no attraction or repulsion, which we can call intermolecular. There is no intermolecular attractions or repulsions among the molecules. No intermolecular interactions. That means this is a very ideal state. Each molecule can move independent the influence of the other molecules. So the pressure exerted by a molecule will be independent by the presence of this other molecules surrounding this one. So this one is also ideal situation, these two. And the fifth and the sixth one, how the pressure is exerted. Suppose this is the wall. This is the wall of the container. These are the gas molecules. Whenever the molecules are moving at random, the molecules having the continuous collisions or suffers collisions with the wall of the container and among themselves. It is obvious whenever someone is running very with a high speed in a mop, there mop present in a room, then this person will suffer collisions with other persons or with the wall of this room. So this whenever these are the two type of collisions. One is wall collision, and second one is the intermolecular collisions. So there are two types of collisions. So among these two types of collisions, whenever we consider the wall collisions, there will be, these collisions are perfectly elastic. Means whenever this molecule collides, there will be no loss of kinetic energy or no loss of this momentum. Momentum remains unchanged, kinetic energy also remains unchanged. So whenever this molecule collide with the wall of the container, the collision of this molecule with the wall is perfectly elastic. So it comes back again after the collisions. So if this one, the momentum is mv, then this one will be minus mv. Means the velocities are vectorial term. It has the sign it has the magnitude and also the directions. Whenever if you consider mb in these directions, in the positive direction, then in this case the momentum will be mv minus mv. M is the mass of this molecule, v the velocity. So whenever there occurs a wall collisions, there will be no change of velocities. No change of velocity. It is remarkable. We shall discuss a much better way. But in case of intermolecular collision, suppose this molecule is going here in this direction, and another molecule going in this direction. So there occurs a collision. This is the intermolecular collisions. So this molecule will move in this direction, this molecule will move in this direction after the collisions. If you consider the V1, it is V2, it is V3, it is V4, then the kinetic energy before the collisions, half m v1 square plus half m v2 square. This is the kinetic energy before the collisions of the two molecules. After the collisions, the total kinetic energy will remain the same, since the collisions are perfectly elastic. So in this case, it will be half m v3 square plus half m v4 square. This is before, this is after. Kinetic energy will remain the same, since the collisions are perfectly elastic. Now we shall consider how the pressure is developed whenever the gas is present in a container. This is also vital. How the pressure is developed. So whenever the molecules are colliding with this wall, the molecule exert some thrust on the wall of the container, and the pressure is developed whenever the molecule just collide on the wall of the container. The magnitude of the pressure depends on the strength of this thrust and also the frequency the molecules are making collision with the wall of the container. So pressure of this gas is exerted. Pressure of this gas is developed due to the incessant collisions of continuous collisions of gas molecules on the wall of the container. So we shall develop the theory in a kinetic in the form of equation. So in that case, we shall use this Newton's law. Rate of change of momentum of all the molecules on the wall of the container will be equal to the force developed by the gas molecules on the wall of the container. So Newton's law we shall apply. Newton's second law. So the last one, seventh postulate is that due to the intermolecular collisions, the velocities are changing, and you will be surprised that per cc of this gas per second time, at least 10 to the power 27, 28 collisions are there. So the number of intermolecular collisions are very, very high. So the velocity or the speed of the molecules are also changing of that magnitude. But the whatever may be the speed of the molecules are changing, the average kinetic energy of the molecules only depends on temperature. Only depends on temperature. That means average, this is average kinetic energy of the molecule is directly proportional to T. If T remains fixed, then average kinetic energy will also remain fixed. So epsilon bar again half mc square. So whenever the temperature is increased, the velocity of the molecules are increased. The thrust of the molecules with which these molecules are making collision with the wall, this is also increased. So if you keep this pressure fixed, then volume will increase with the rise in temperature. Or if you keep this volume fixed, then pressure will rise with the increase of temperature. This is the Charles law. And also Boyle's law is also verified from this postulate. If you reduce this volume of this container, then there will be more frequency of the collisions. More frequency of the molecules that collide with the wall. Naturally, if you reduce this volume, pressure is increased. Means volume is inversely proportional to this pressure, which is the Boyle's law. So these postulates not contradict. The postulates are not that they are contradicting the experimental results. They supports the Boyle's law, Charles' law, etc. Though it is the assumptions or the imagination. Every theory, whether theory is first or the fact is first, it is a debatable thing. But someone thinks that theory coming first, and then the scientist will go in search of the verification of his theory. Theory is the imagination. So from this we can consider one thing, that is RMS speed. RMS speed. Idea of root mean square speed. Root means square feet. It is mathematically C(A1S) we can write C(A1S) mean RMS, root mean square speed. RMS, root mean square speed. Mathematically it could be designated as C square bar. This is root, this is mean, this is square, and this is speed. So RMS speed would also be mathematically written as root over C square bar. Root, mean, square, and speed. We can have an idea. Automatically whenever we are going to develop the kinetic equation, automatically this RMS speed is coming up. We know that again one thing I can also here state that it is also very important. Though the speed of the molecules are changing incessantly, continuously, but a definite number of molecules must have definite speed within a small range at a given temperature. This is very peculiar. Though the velocities of the molecules are changing continuously, incessantly, still then, definite fraction of the molecules will have a definite velocity within a small range at a given temperature. If temperature remains fixed, then definite number of molecules will have a definite velocity within a very small range, within a very small range. So average kinetic energy we can write say N1 epsilon 1. N1 is the number of molecules each having the kinetic energy epsilon 1, and this is N2 epsilon 2, number of molecules having the kinetic energy epsilon 2 at a given temperature. Temperature is fixed, plus N3 C3 plus dot and divided by the total number of molecules. N equal to N1 plus N2 plus N3 and so on. So if we convert this kinetic energy in terms of the speed, then it will be N1 into half N C1 square. N is the mass of each molecule. C1 is the speed of the molecule of N1 number of molecules. Plus N2 into half M C2 square plus N3 into half M C3 square plus divided by A. So we can write half N common and N1 C1 square plus N2 C2 square plus N3 C3 square N3 C3 square plus dot divided by A. And this term within the bracket, here to here is called the mean square velocity. And that we can write a half M C square bar. Mean square velocity. Mean square speed. Or we can write, half M C RMS square. CRMS square equal to this term. So actually CRMS equal to root over of C square bar, and this one equal to N1 C1 square plus N2 C2 square plus dot and divided by A. So there is another type of speed that is called the average speed of the molecules, but the RMS speed having more theoretical or more fundamental, more theoretical more accurate than the average speed. Since this epsilon bar is coming from the temperature. Temperature is a fundamental property, thermodynamical property. So from thermodynamical properties, T is coming and T is related to epsilon bar, and whenever we are doing this full-fledged explanations of this epsilon bar, automatically CRMS is coming. So CRMS is more fundamental than the average speed. RMS speed is more fundamental than the average speed. Not only that, we can have the concept of temperature. Concept of temperature. Concept of temperature from these assumptions of kinetic theory, from the postulates of this kinetic theory. How the concept of temperature is coming up? So epsilon bar is proportional to T, or you can say epsilon bar equal to some constant into T. So whenever the T is increased, temperature, whenever the T epsilon average kinetic energy increase, T is also increased. Epsilon bar is increased, T is increased. And not only that, whenever the molecules are moving at very high speed, temperature is also high. Or conversely, we can say whenever the temperature is high, then motion or the speed of the molecules are also increased. And where absolute zero temperature, whenever T equal to 0, absolute zero temperature, then whenever T equal to 0, then epsilon bar equal to 0, these molecules are not moving, all the molecules are at rest. Whenever all the molecules are at rest, that temperature we can assign the absolute zero temperature. Now I am coming to the formulation. Now I am coming to the formulation of kinetic equation. Kinetic equation, and it is PV equal to 1/3 n C RMS. M is the mass of each molecule, P the pressure exerted by these gas molecules on the wall of the container, B the volume in which the gas is present, and N the mass of each molecule. N it is written as capital A. N is the total number of molecules present in this gas vessel, and CRMS, which I said, it is the RMS speed, root mean square speed. So, in order to formulate this one, we can take a very simple shape of this vessel, simple shape of this container, and simple shape that we can use here, the cube. Cube is having the highest, next to highest, the symmetrical in nature. Most symmetrical is spherical, sphere, and cube is second best symmetrical shape. So it has actually this. It is cube. We can draw this cube by this two square. First right, and then the corners are joined. So this is the cube. The length of this each side is A. So this volume of this cube is L cube. Volume of this cube is L cube, and the surface area, total surface area, total surface area. Total surface area equal to 6L square, as the cube is having the six walls, each wall having the area L square, so 6L square. Now we like to reduce the speed equal to 1 per mx square. Very popular kind of equation, and this is the mathematical form of this kinetic theory. Every theory must have the mathematical form. With this mathematical form, we can explain the other properties of this gas quantitatively. So this equation is very important. How could we formulate this equation? Very simple. Here suppose let us consider N1 molecules have speed C1, N2 molecules have speed C2, N3 molecules have speed C3, and so on. And total N is the total number of molecules, N1 plus N2 plus N3 plus. And we shall have to consider the three-dimensional velocities of this molecule. Let us consider one molecule. Of this N1 type. That means this molecule is having the resultant speed C1. If we resolve the resultant speed C1 into their component velocities along this x-axis, y-axis, z-axis, then actually C1 square equal to U square plus V square plus W square. Say this is U in this direction, and in this direction it is V, and in this direction it is W. These are the velocities. It is to be remembered. These are the velocities having the magnitude as well as the direction. But this one having magnitude but no direction. So this is speed, and these are the three velocities. This one is the speed, resultant speed of this molecule in this group N. So whenever if suppose this is the one, this molecule is coming with this velocity U and striking this one, and this one collision is perfectly elastic, so it is momentum mv. When it is coming back, it is minus mu. Mu is the momentum along this x directions, and minus mu the reverse directions along this x-axis. So minus sign is given as the direction is reverse. If you go this way, then positive. If you come this way, then negative. So this, for one collision, whenever this molecule, actually what is our motto? We shall have to develop the Newton's second law. Means of what will be the total rate of change of momentum for all molecules present in this vessel, and that total rate of change of momentum of all molecules in all directions will give you the developed force, or the force developed by the molecules on the wall of the container. This is the pressure, this is the gas pressure. So actually change of momentum of a single molecule in the x direction is equal to mu minus mu. change means difference, and this will be equal to twice m u, twice m u along this x directions. Similarly, if we consider the rate of, if we consider the change of, so what will be the rate of change? The velocity of this single molecule is c1, means, or you can say the u is the velocity of this molecule in x direction in unit time, in 1 second, say. So the molecule, whenever this molecule undergo this L distance, there becomes one collision. Then again coming here, another collisions. Again going there, another collisions. So after traveling L distance, the molecule suffer one collision. And the molecule in this type, in 1 second or unit time, it will move this u distance. So u by L is the number of collisions suffered by this molecule in 1 second. Number of collisions it suffered in 1 second. 1 second. So for this molecule along this x direction, if we consider, then rate of change of momentum, of this molecule along x direction, is equal to this and these two multiplications, this one and this one. So it will give you twice m u square by n. And so rate of, for the same single molecule along y direction, it is equal to twice m u, twice m v square by n. V is the component velocity of this molecule along this y direction. Along this z direction, it is twice m w square by n. So whenever consider the resultant total rate of change of momentum along these three directions, so then we shall have to sum up. We have to sum up all these three. So the rate of change of momentum means change of momentum for every time. Rate of change of momentum of the molecule equal to sum of these three. So whenever this we are summing up these three, twice m by l common, and it is u square plus v square plus w square, and these are the speed, these are the velocities. This is the velocities along this x direction, y direction and z directions, and this one will give you twice m l and c1 square. C1 is the speed, resultant speed of this molecule of N1 type. So similarly, if we this type of molecule, number of this type of molecules is N1. So for N1 molecules molecules, the rate of change of momentum for N1 molecules, it will be twice M N1 C1 square and divided by N. So in this way, if we consider change of rate of change of N2 molecules, this will give you twice N2 and C2 square and divided by N. And for N3 molecules, this will be twice N3 and C3 square divided by N. And so on. If we now consider the total rate of change of molecules, total rate of change of all the molecules due to their wall collisions, then it will be total rate of change of momentum for all the molecules. This will be equal to twice M, sum of these three, 1, 2, this twice M by N, and suppose N is multiplied, then it will be the N1 C1 square, first type, and second type is N2 C2 square, and third type N3 C3 square plus order, and N is here multiplied, so N is here to be divided. And this term within the bracket is the mean square speed. So this could be written as twice N and C RMS square and divided by N. The term within the bracket, already I have defined, this term within the bracket is equal to the mean square speed, or you can say square of RMS speed. So this is the total rate of change of momentum, and according to the Newton's second law, Newton's totally ruled the science for at least 400 years. 400 years Newton ruling the science. So according to the Newton's second law, this one will be the force developed by the wall collisions of the molecules of the wall. The force means pressure into surface area. So pressure, suppose this one will be equal to pressure P, and surface area is 6L square. So from these two, equating the Newton's second law, we have this L coming here, so this will give you, we are coming this equation. If we simplify, then 2 will go there, and here L square here, so this P and L cube becomes L cube, L square, and L cube means B, the volume of this gas, equal to 1/3 M N C RMS square. So this formula is being developed. N is the total number of molecules present in this vessel. So kinetic equation has already been developed. Another form we can write this one. You know this P equal to 1/3 and M divided by V and C RMS square. N is the mass of each molecule and total number of molecules N. Then M into N, the mass of this gas molecules, and mass of this gas molecule, and it is the volume of this gas. So this by this will give you mass by volume will give you the density of this gas. So this P we can write also 1/3 rho and C RMS square. Rho is the rho equal to N divided by V, and it is the gas density. It is the gas density. Rho is the gas density. So the kinetic equation is being developed. So this equation is very important, and which I have told earlier that whenever the theory is developed, from these postulates we are coming to a mathematical formulation and have a kinetic equation. Our kinetic equation is this one, and from this equation we can do several things which is not possible to determine experimentally. Suppose the magnitude of RMS speed. What will be the magnitude of this RMS speed in a gas? This is not possible to determine, but we can calculate easily from this theory. So theory will give you much data which are predictable, which are not possible to determine experimentally. Theory is much more superior than the experimental facts. So here, suppose calculation of or the magnitude of CRMS. Magnitude of CRMS. So magnitude of CRMS for one mole gas, we have a PV equal to RT, ideal gas solution. As the postulates in kinetic theory, we have assumed ideally there is no intermolecular interactions, molecules have no volume. These are the assumptions of this ideal gas. So this ideal gas is applied for 1 mole, and this is PV equal to RT. So whenever 1 mole of this gas is there, then PV, instead of PV we can write RT equal to 1/3 and M mass of this each molecule, and this total number of molecules will be equal to the Avogadro number. As you know, 1 mole of every substance will contain Avogadro number of particles. So actually M Avogadro number, N is the Avogadro number, and C RMS. So instead of PV we can write RT, and instead of N it is the Avogadro number. So this one will give you 1/3 and mass of each molecule, and Avogadro number, this 2 is the molar mass of this gas, molar mass of this gas. So actually CRMS equal to root over of 3 RT divided by M. 3 RT by M. So from this we can easily we go to the conclusion that the CRMS, root mean square speed, is inversely proportional to root over of molar mass. That means heavier gas will have this molar speed, lighter gas will move with a faster speed, and with the rise in temperature for a particular gas, with the rise in temperature, RMS speed is also increased. We can calculate a simple problem. One problem. Calculate the RMS speed of oxygen molecule. Oxygen molecules at 27 degree centigrade. So CRMS, we can put here CRMS equal to root over. It's here 3. If we put this R in joule, then 8.31 joule mole inverse Kelvin inverse. And the temperature 27 degrees centigrade means 30 Kelvin, 300 Kelvin. 27 degrees centigrade means 300 Kelvin, and whenever we put this R in joule SI unit, then M for oxygen, molar mass of this oxygen is 32 into 10 to the power minus 3 kg mole inverse. Kg to be put up SI unit, and if we mole inverse cancel, Kelvin inverse Kelvin cancel, and joule equal to this kg into kg meter square second inverse 2. So kg and here kg will cancel, and root over m square. So this will give you 483.445 and meter per second. So the oxygen molecules are moving around us. We are in a sea of this oxygen and nitrogen gas. So oxygen molecules are so small. Oxygen gas molecules are also colliding on the body, on the surface of the human body. Still we are not feeling, since the oxygen molecules are very small in size. So this impact is also very small. So this oxygen molecule 27 degrees centigrade means almost room temperature. At this room temperature, this molecule moving such a high speed, about half kilometer, roughly you can say half kilometer per second. Half kilometer per second, so such a high speed, no train or nothing else could have achieved such a high speed. Half kilometer per second means from here to Calcutta, if we take this 250 kilometer, then for this oxygen, this time will be only the 500 second. 500 second means less than 10 minutes. Can you imagine? The gas molecules are moving how much high speed? But however, whenever the oxygen will move, it will suffer collisions, and maybe from that collisions it will rebound and cannot go straight. So another thing I here mentioned the kinetic energy. I have an expression of average kinetic energy. Average kinetic energy, again we consider 1 mole ideal gas, and the equation is PV equal to RT. And in this case, instead of PV, we can write RT. So RT, kinetic equation. This is the kinetic equation. Instead of PV, we can write this RT equal to, if we write a truth 2 by 3 and Avogadro number, whenever 1 mole ideal gas we consider, it contains Avogadro number of molecules, and this one is half MC RMS square, and this one is the average kinetic energy. So this will give you the 2 by 3 Avogadro number and epsilon bar, average kinetic energy. So average kinetic energy equal to 3 by 2 to R by Avogadro number into T. This term within the bracket is constant. So average kinetic energy is directly proportional to temperature in Kelvin scale or absolute scale. So R by Avogadro number, sometimes called the K. K is called Boltzmann constant. Boltzmann constant. Very important. They are actually Maxwell, Boltzmann, Arrhenius. They are the father of this chapter, physical chemistry. They are the originator. So this has been given the name R by Avogadro number will give you the Boltzmann constant, and its value is, if we put there, then its value one point three eight into 10 to the power minus 10 to the power minus 16 R molecule inverse, not mole inverse, molecule inverse, molecular inverse. 1.38 into 10 to the power minus 16. R you can put in R. Avogadro number, put 6.023 into 10 to the power 23. Divide these two, you will get its magnitude of K. K is found to be 1.38 into 10 to the power minus 16. So this PV. So the average kinetic energy, if we consider the average kinetic energy per mole means which contains the Avogadro number of molecules, then this to be multiplied epsilon bar multiplied by the Avogadro number. Whenever it is multiplied by the Avogadro number, it will be 3 by 2 for n molecules, n moles, for n moles of the gas, this average kinetic energy equal to 3 by 2 n RT. 3 by 2 n RT. N is the number of moles of this gas present in this vessel. So we can do another calculation, calculate the kinetic energy, calculate the kinetic energy of 8.5 gram ammonia at 27 degree centigrade. So this average, kinetic energy will be equal to 3 by 2 N of T. So it is 3 by 2 into N. How much will be the number of moles? Molar mass is 17 gram per mole for this ammonia. Ammonia having the formula NH3. So the N equal to 8.5 gram and divided by 17 gram moliners. So this will be 0.5 mole. So here instead of N we can write 0.5 mole. And R equal to, if we put here 2 calorie mole inverse, it can be inverse into 300 calorie. And this will give you very simple calculations. Whenever we put this value of R 2 calorie, then calculation is very simple. 2 and 2 cancels, and it will give you the 450 calorie. Now last one, the gas loss could also be reduced. The gas loss, reduction of gas loss, Walsh law, Charles laws, Avogadro laws, and Graham's laws, etc. The reduction of gas loss. Very simple. If we consider the 1 mole, say this PV equal to 2 by 3, and it is N into half M C RMS square, and this one, so 2 by 3 into N epsilon bar. And epsilon bar in my postulate number 7, I have already said that epsilon bar is proportional to T or equal to K dash T. K dash is some constant. So if we put here this one equal to 2 by 3 total number of molecules present in this vessel and K dash, this is constant. This one is constant. Within the term within the bracket is constant. It is the total number of molecules present in this dash, and K dash is proportionally constant T. So PV equal to some constant to T. So if you keep this T constant, if you T the constant, then full right hand side is constant. Then in this case PV equal to constant. Or V equal to constant by P, or proportional to V proportional to 1 by P. This is the Walsh law. V is inversely proportional to the pressure. If you increase this pressure, volume is decreased at a given temperature, mind that. And for a given amount of this gas, N is fixed at a given temperature, T is constant, right hand side is fully constant, so P is proportional to 1 by P. Charles law again verified. Charles law say V, we can write V equal to 2 by 3 N K expressed by P and T. Whenever the pressure is fixed, whenever the pressure is kept fixed and the total amount of this gas is fixed, then the term within the bracket is also constant, then P is proportional to T, and this is the Charles law. This is Charles law. If you increase this temperature, volume will also be increased. We can also verify the Avogadro's law. Avogadro's law. Formerly it is called the Avogadro's hypothesis. Now this hypothesis is verified in different way, different fashions, and it is now confirmed. Avogadro number and Avogadro hypothesis, and so Avogadro hypothesis is turned into Avogadro's law. Now it is a law. So what this law states, at a given temperature pressure, equal volume of all gases will contain equal number of molecules. At a given temperature pressure, equal volumes of all gases will contain equal number of molecules. This is to be verified from this kinetic equation. Very simple. Say for, let us consider the two gases at a given temperature, pressure and volume. Since pressure and volume fixed for these two gases, so we can write for this first gas P1 V1 equal to 1/3 M1. M1 the mass of the first type molecules. M1 is the mass of the first type, mass of these molecules of this first type gas, and so here it is N1 into C1 square. And for the second gas P2 V2 equal to 1/3 M2 and N2 and C2 square. C1 is the RMS speed of the first type molecules, say R2 is the RMS speed of the second type molecules, and N2 is the number of molecules in second type, number of molecules present, and N1 present a number of molecules. And if we, and again, so another thing is that since the temperature is same, the kinetic energy will also be the same. So kinetic energy same means epsilon 1 bar equal to epsilon 2 bar. So half M1 C1 square equal to half M2 C2 square. This is equation number. Now same pressure temperature, so it is also same PV and it is also same PV, same pressure volume. Two gases are at the same pressure volume. So PV, so 1/3 M1 N1 C1 square equal to 1/3 M2 N2 C2 square. This is say equation number A, and this is say equation number B. If we divide A by B, then A by B, then it will be A1 equal to N2. This half cancel, 1/3 cancel, and if you divide left hand side by left hand side, right hand side by right hand side, then N1 equal to N2. What does it mean? At a given temperature and pressure, two gases having the volume V have also the same number of molecules. This is the Avogadro law. And the Graham's law, last one, the Graham's law. Graham's law states that the rate of effusion is inversely proportional to the molar mass of this gas. So rate of diffusion or effusion is proportional to C RMS. Greater the value of RMS, greater will be the diffusion of this gas from this small hole. So RD is proportional to, instead of RMS you can write 3 RT by E. This is the expressions of this RMS. So proportional if at a given temperature, if you keep this temperature, then it will be proportional to 1 by A. So this is the Graham's law. The heavier gas will diffuse less than the lighter gas. Lighter gas means N is small, the rate of diffusion is high. So this is all about the kinetic theory of this gas. Here first we stated the postulates or assumptions, and then we formulate one kinetic equation, mathematical form of this theory, and from this kinetic equation we have several expressions of the RMS speed, expressions of the average kinetic energy, expressions and the verification of the experimental laws, the Boyle's law, Charles' law, Avogadro law, and also the Graham's law. So this is all about today's video lecture. Lecture may be lengthy but very easy, and the beginners of the physical chemistry can easily grasp the idea, and I will be very much delighted if you all subscribe this video and encourage me to do more video in future on this chapter, kinetic theory and gaseous state. Okay, thank you all.